It's a pleasure to be here, be there, be remotely viewing by you and with you. Just a small correction. I am not a radio talk show host, Greg. I am a radio talk show pundit and extravaganza host. No, I'm not. I'm none of those. I do have a podcast, and I have had on Chien-Simons. And for our Father's Day episode, you can see that on my YouTube channel, link below. And next year, I hope to have Marilyn on Mother's Day because I had Jim on Father's Day. So check that out, along with many of our colleagues and friends around the world of astrophysics. So today, I'm kind of using this pun and one of Jim's favorite words, peregrinations, which I had to look up. But it's appropriate for the topic that I'm going to be talking about today, which relates to this old joke. A policeman sees this guy who's drunk looking on his hands and knees underneath a streetlight. And the cop says, "What are you looking for?" He says, "I'm looking for my keys." And the cop said, "Did you lose them over here?" He says, "No, I left them over there by the bar, but this is where the light is." So we have to search as astronomers and astrophysicists where the light is. And today I'm going to talk about two sources in particular of natural astrophysical light and multiple forms of human-made, astrophysicist-made artificial light sources that should help us illuminate fundamental issues in physics and cosmology. So I'm going to begin with a literally 2-second overview of the cosmic microwave background radiation and why polarization is so important, why it captures so much attention. And that's actually the main goal of the Simons Observatory, is to do all these cool things kind of on tier one of the cosmic microwave background's resume, is that it can be used to divine properties of the universe, both at its earliest moments and its future, and also in its evolution, since it is essentially the earliest, the oldest fossil relic in the form of microwave radiation that reaches our telescopes. And it's been used now for since 1965 as perhaps one of the most precise probes of how the universe is organized, how the structure is comprised of, and and how and where it might be going next. Actually, as I say, I'm not going to talk much about that. The subject is so rich that the majority of the science goals that we are pursuing with the Simons Observatory, I am not going to cover because those are, in some sense, our primary, as I said, headline goals. What we're really doing with the Simons Observatory is everything that's shown here, which is looking for the evolution and composition of the universe subsequent to the formation, at least, of the cosmic microwave background, which happened about 380,000 years after some kind of origin event. We don't know for sure if that was a singularity. I've had conversations with Sir Roger Penrose recently and many other people who claim that there are differing alternate viewpoints on how the universe could evolve. So that's just a plug for my podcast. I'll beg your forgiveness and forbearance on that. But I do want to point out that one of the leading candidates for at least the origin of structure, if not cosmogenesis itself, is known as inflation. Inflation explains a great host of problems, as we often find with cosmology. One solution to an outstanding problem will lead to many more problems later on down the road. And it's our job as experimentalists and theorists to understand the limitations, the lacunae of the theory, but also to make progress towards patching that up and maybe even illuminating new problems that we will search under cosmic lampposts in answer to. So these are the headline goals of the Simons Observatory: to understand dark energy, even solar system projects looking for so-called Planet 9. We even have a plan to image Jim and Marilyn Simons also have asteroids floating around in the asteroid belt. My personal goal would be to observe those and see what resources they may have in store for cosmologists. So again, I'm not going to talk much about it, just to say that if you had microwave eyes and you journey down to our site in Chile, this is the Simons Array, which is partially constructed and is about to kick off science observations, you would see a very boring orange glow with pure microwave eyes. Actually, you wouldn't see orange, you would just see a uniform glow pretty much in all directions. And only when you reveal the uniform glow, the average temperature, the famous 2.7 degree black body, 3 Kelvin black body, as we round up, would you see these fluctuations, which are so exquisitely measured by satellites such as Planck and WMAP and many other instruments around the Earth, from the Atacama to the South Pole, and even in space. And of course, one of the great mysteries is how do these perturbations get there? If you start with a universe that's uniform, homogeneous, and isotropic, how do you then evolve into something that has such rich structures, such as planets, cosmologists, etc.? Well, one of the underlying motivations for inflation is how well it can study and explain, rather, the origin of perturbations itself in the form of what are called primordial perturbations, which themselves are the result of the excitation of a primordial field, a scalar field, not unlike the Higgs in some way. Some claim it might be related to the Higgs. But nevertheless, a scalar field known as the inflaton is conjectured to have quantum jitters, fluctuations, which would then release or would cause an imprint upon the structure of space-time itself to give it curvature, to give it ripples, to give it perturbations. And those perturbations would then seed the great assemblies of dark matter that would later agglomerate to form structures such as galaxy clusters and individual galaxies, stars, planets, people, and cosmologists. So that's kind of the overall structure of the CMB and why it's so interesting. But the question that inflation doesn't answer is how did it itself get started, if indeed it did occur? And to answer that question and to get some more insight into the initial moments in the universe, the field starting in the early 2000s, actually the 20th anniversary of the creation of an experiment called BICEP, which we started at Caltech to observe the potential imprimatur of inflation, which would be gravitational waves propagating. The resultant concomitant fluctuations of the inflaton will spawn gravitational radiation in the form of what are called primordial gravitational waves. And later on, as the lower right panel indicates, would reveal themselves through an imprint known as B-mode polarization. And again, this is one of the headline motivations for the Simons Observatory, for the Simons Array. And this is about it that I'm going to talk about it. So sorry to disappoint you. If this is what you want to hear about, you can tune out. But I implore you not to, because just as the excitement was gleaned and garnered from the announcement that we made prematurely in 2014 on St. Patrick's Day, 2014, almost 7 years ago, we announced that we discovered this swirling, twisting, curling pattern of microwave polarization known as B-mode polarization. We made this announcement back in 2014, as I said, BICEP 2, and it caused great fanfare, including the paper of record, the San Diego Union Tribune, but not that alone. In addition, it was featured around the world on CNN, et cetera, et cetera. And the question as to the reality of that signal was questioned almost immediately by colleagues around the world and friends. And it resulted in a book deal. That's the most important result. No, it actually had many implications on cosmology, not the least of which was to start the motivation for doing a thorough job, not only characterizing the universe's primordial perturbation spectrum, but also looking past its dust jacket, so to speak, to reveal properties that might masquerade as this imprimatur signal, namely microscopic particles of dust. And these microscopic dust particles could obscure, and in fact, they can compete and perhaps even overwhelm the faint, tenuous signals of the microwave background that we are hoping to be revealed as an indirect piece of evidence towards the inflationary paradigm. Again, we don't have direct capability to directly measure these gravitational waves in our laboratories. And so we're using the CMB's last scattering surface as a type of film, a photographic film, onto which we expose waves of primordial gravity. And in so doing, we hope we might reveal the presence of inflation, if inflation took place, and if inflation was energetic enough to spawn these perturbations that would produce an observable size of B-mode polarization, none of which we know to be true. And that's why, as my advisor used to say, we call it research. Of course, we had to retract this claim. It was actually featured in the Quantum magazine soon after. I mean, this is only about 6 months after the discovery did we effectively have to retract that with BICEP 2 and realize that we need to be a little bit more. We had always assumed that this could be the case, that dust could contribute. But in fact, what BICEP did in a technological tour de force is make these exquisite measurements of dust effectively. But now we know to go further, we must measure dust and the CMB. So we take advice from Mahatma Gandhi, um, who said the seeker after truth should be humbler than the dust. The world, and we could say the universe, crushes the dust under its feet, but the seeker after truth should so humble himself that even the dust could crush him. Only then and not until then will he have a glimpse of truth. And this is from his experiments with truth. So he was an experimentalist. I didn't know that, but his imprecation is well heeded, and in fact, that drives a lot of the design of the Simons Observatory, which I won't be talking about. But I did talk about it 5 years ago exactly, next month, and I know that because right after I gave my last talk at the Simons Foundation, that one was in person, so I could partake of the fine wine and cheese therein. We found out that we had received preliminary approval to start constructing the Simons Observatory. So I'll turn to that after our next topic. So what I'm going to talk about today is not these really incredibly potentially transformative measurements of fundamental physics that would be the result of projects like the Simons Observatory and Simons Array, and that is geared towards measuring these primordial perturbations. Instead, I'm going to talk about an exotic phenomenon, which I should point out is also very high risk, but it's in some sense to me perhaps even more high on the list of potential reward for a reason that I'll explain as we go on. So I don't have to explain to this audience the importance of Chern-Simons theory. I'll just put into a couple of slides some references to my friend Stefan Alexander. There's Jim Simons. How often do you get to hear from the man himself talking about the import and impact of Chern-Simons theory? But it turns out that it has wide applicability from everything from exotic materials, insulators, topological insulators, to string theory, as Edward Witten has shown, but also to cosmology, as I'll talk about, which has been realized now for over 30 years. And even a tentative claim or 2 or 3 has been made of its detection. So, the mathematics behind it, for those of you who are more mathematically inclined, will just note that the Chern-Simons 3 form can be cast in a way that is typically referred to in its most useful form for physicists, as shown on the right, from a personal communication with Greg and Jim and I, and that is to express it as a Lagrangian or to an action density. And that action density reveals the presence of a couple of potential effects. One of which is that the resulting field equations for electromagnetism could in fact be not only in violation of parity symmetry, but also in violation of Lorentz invariant symmetry. Now, there's nothing more closely held to the physicist's heart than is Lorentz invariant symmetry. And I want to talk about both of these next. And the reason that this is so much more potentially transformative to me than even a detection of inflationary generated gravitational radiation, B modes, primordial B modes, is that it would potentially upend our most closely and cherished held beliefs about the fundamental symmetries of nature. So you can look into a little bit more detail. You can find plenty of videos on the web from the foundation elsewhere, and learn about these applications. But I'm going to point out several of them and how they impact our search with Simons Observatory and other projects in the microwave background field. And then I'm going to also talk about another kind of lamppost, namely using exotic galactic nuclei, extragalactic nuclei, as another lamppost, which could reveal the presence or lack thereof of these types of phenomena that are intimately related to this Chern-Simons 3 form. So I mentioned Lorentz invariance violation, and I'll say that this is perhaps the dearest and nearest thing to every physicist for over a century now, and that's because both general relativity and the standard model of particle physics rely on Lorentz symmetry, which is expressed loosely as symmetry under boost, under rotations, under translations of space-time, under a set of groups, of Lorentz groups, that are leaving the equations of motion, of mechanics, of particle physics, and of general relativity completely unchanged. And that has propagation effects downstream, as I'll illustrate in the next slide. One thing I point out, and I've had this conversation with many people on the podcast, from Frank Wilczek just this week or last week, to Sheldon Glashow and beyond, and that is this issue of quantum field theory and the reconciliation thereof with general relativity. In other words, a quantum theory of gravity not being present. I talk about that quite often, and if you've turned into the podcast at all, you've heard me kind of harp about this, and so I won't do so now, but I'll point you to a long playlist of discussions with some of the most eminent physicists that are, actually make the mistake maybe of coming on the podcast, but I think you'll enjoy it. And so I want to point out that here's the, kind of just a cartoon by my friend Matt Muse, professor at Cal Poly Pomona, up the interstate here in California. And he made this nice kind of cartoon diagram that everything in physics that we hold as sacrosanct is predicated on the three vertical blue shaded pillars of quantum mechanics, of Lorentz symmetry, and of curved spacetime. And on top of that is structured the standard model, GR, Newtonian gravity as an extension of GR, Newton's laws as an extension, if you like, of the standard model, as with electromagnetism. And so the question is, what would happen? And that may or may not be predicated and standing upon an ultimate foundation known as a theory of everything. I always point out, I get emails every day about somebody's got a new theory of everything. I've never once had someone say, I have an experiment of everything. I'm really looking forward to getting that hint. But maybe, indeed, the Simons Observatory is the droid, is the experiment I've been looking for my whole life. And that is because we could perhaps reveal the breaking, the slight, we know it has to be slight, but there could be a slight violation of Lorentz symmetry invariance. And in so doing would create a cascade, an effect downstream that might reveal itself in the laboratories, perhaps, although it's not likely, and that's been ruled out, but over much larger cosmic distance scales, the scale of active galactic nuclei, the scale of the CMB itself, the oldest fossil relic light in the universe, could be manifest, and we could measure that, and that'll be smoking gun signature of new physics, as illustrated cartoonly here. The other thing that this Chern-Simons term type addition to electromagnetism does is it admits what's known as not only as Lorentz symmetry violation, if it indeed depends on reference frame or on some direction in space that I showed in the original slide, this vector p mu, 4 vector p mu, but it could also almost mandatorily have to violate parity symmetry invariance. And that's less controversial because we know a variety of aspects of nature in which parity symmetry, the symmetry between mirror physics and itself, and physics not in a mirror, if you like, is violated. Here are some examples on the left. I'll point out the Simons collaboration on the Origin of Life project has a project to understand why are molecules mostly right-handed versus left-handed. I hope I get that right. And why are neutrinos left-handed, not right-handed? And so the question is, does physics look the same in a mirror? Used to be another sacrosanct feature of physics. And yet we know since the 50s now that that's not true. And so the extension from these lists that I'm showing here on the left to the cosmos will be made manifest in just a minute. And that's what the initial claims that I'm going to shed some polarized light on will be focused on right after this. So the question of whether or not parity is violated, it is violated for sure in weak interactions. And so since the 1950s, T.D. Lee and Frank Yang, who I'm trying to get on the podcast, and with Jim's help, it may occur someday. But the question is parity violated? And a very, very unique and ingenious experiment was conducted by Chien-Shiung Wu at Columbia University. This is now going back to the late 1950s. So it's predicted by Li and Yang, and then it was observed less than a year later. In fact, apocryphal as it may be, there was a story that Wu did it in sort of a weekend. She was able to do this experiment incredibly rapidly. And what it showed is that for certain processes in physics, namely the emission of beta radiation, which is just a fancy name for electrons, in a mirror behaves in such a way that we can distinguish the direction or handedness. In this case, we use a spinning cobalt-60 nucleus, which, if you like, when viewed in a mirror, should reverse the direction at which it emits beta rays. But in fact, that's not found to be the case. So we can say that parity is not conserved because the mirror image if you like, should show an opposite direction, and we don't see that. We see a similar direction, which indicates parity is violated at a low level in the weak sector. And so, just as with Spock down there, it's quite fascinating development. And for this and for other discoveries, Li and Yang were awarded this gilded medallion here. But unfortunately, the famous Chien-Shiung Wu was not. But I'm happy to report, this is some small consolation, she is receiving this year a forever stamp. So, I don't know which is better. I think, forever is a pretty good thing. Nobel Prize only lasts for a couple of days, I'm told. But her stamp is coming out this year. It's a great honor. I'm actually Twitter friends with her granddaughter, who is a reporter, I believe, for the Washington Post, it turns out. So anyway, it's a fascinating story. And my question is, and many people have asked this question, it's not unique to me, is if the weak force violates parity, and if electromagnetism is unified with the weak force to make the so-called electroweak force, then would it be possible at early enough times to manifest a violation of parity in electromagnetism? And our best, if not only hope, might be to use the cosmic microwave background to divine out whether or not electromagnetism also violates parity conservation, as does the weak force. So how do you get a violation? Well, you in New York City know you park in the wrong place and you'll get a violation. But I know, there it is, CPR, cosmic polarization rotation is the acronym CPR, and that's what we use. It also stands for courtesy, professionalism, and respect, apparently. But how would you get that in the microwave background? Well, applying these laws, this is from a very, very famous, well-known paper by Sean Carroll, Field, and Jakiv from 1990. What they did is they added that three form, if you will, the Chern-Simons term. And if you add it to the ordinary electromagnetic Lagrangian that's shown in the upper left, you get a new term, which is the Chern-Simons term. And then if you just derive Maxwell's equations, which is a standard, graduate level exercise from a Lagrangian, derive the Maxwell's equations, you get these four modified Maxwell's equations, as shown in the center there. The new terms are shown with this underline, and they have this peculiar additional feature in that the curl term for curl cross B, that term acquires a term that depends on this four vectors time component, that's P0, and also on its spatial component. So it's vectorial XYZ component. There's some direction in space it points that will lead to a direction dependent speed of light. And that will depend not only on direction, but also on the polarization of the electromagnetic field, E, capital E here, with respect to this vector's orientation in 3 space. So you get two effects. You get a time-dependent effect, a pure time effect, and you get a vectorial effect, this P term, which can then couple to these electromagnetic fields. And when you write out what is the resulting dispersion relation, it goes from the familiar frequency equals the speed of light times the wave number. It goes to that and it gets modified. It's still that term CK for left-handed circular polarization, but for right circular polarization, it requires a tiny bit of symmetry breaking. And that symmetry breaking parameterized by epsilon, we know it to be small, but the effect is that it rotates the plane of polarization. And so we call such a plane of polarization rotation, we call that birefringence in the laboratory. And now we're saying the vacuum of space-time has this property that it's encoded, encrypted. Not only is space filled with asteroids named after Jim Simon and Marilyn Simons, but it's maybe filled with this kind of vacuum birefringence term. And that will cause a rotation of the plane of polarization. So refringence is really like refrangence or refracting, and that means it kind of acts like a lens. And the bi means it has two different types of indices of refraction, one for vertical polarization and one for horizontal polarization. It's typically found in the substance called Icelandic spar, and allegedly it was used for navigation. by the Vikings, et cetera, to get to, New York City or wherever they got to. But in the recent years, we cosmologists look at this cartoon on the right there. So if the universe starts off with a certain amount of polarization in the CMB's last scattering surface, which we know to be true, then by the time it gets to our detectors, these vectors of polarization will rotate by some amount given by the amount of parity violation, which in turn is given by this Chern-Simons term. So this paper from 1988 is the earliest evidence for it. It was actually in the context of primordial magnetic fields, not necessarily, and perhaps in the context of what's called an axion, which is a candidate for dark matter, which we are also looking for at the Simons Observatory. But the net effect is that depending on how far the photons travel and how strong this Chern-Simons coupling term is, the polarization plane will rotate by a macroscopic angle, shown here as beta. And that term, as I said, this is predicated on this addition of a Chern-Simons term to the Lagrangian of electromagnetism, just propagating through, doing the math as I showed before, we get out this term where we would predict a difference in velocity between left and right circular polarization, which leads to a rotation of the plane of polarization. So this is the subject of the major headline claim in today's abstract, which is that there was a claim of a detection at 99.2% confidence that the universe does in fact have this type of behavior, that the plane of polarization does rotate by a small degree, 0.3 degrees, with an uncertainty 0.14 degrees. And this, as in the case of BICEP, led to quite a stir of headlines. You'll see a couple of headlines today. And it really caught the attention of many people. Of course, it caught my attention, and we dug into it really deeply, and we're preparing kind of a response. These are our friends. Yuto Miyame is one of our colleagues on the Polar Bear and Simons Array project, and Ichiro Komatsu is a legendary cosmologist who is a member of the Simons Observatory External Advisory Committee. So I have to be nice to, no, I don't. He's a wonderful scientist, and he will, of course, welcome the scrutiny that we are providing to this rather extraordinary claim. So once again, this is the phenomenon we're looking for. It was claimed to be detected. A vertically oscillating polarization will then get rotated by some amount depending on the strength of the interaction. This Chern-Simons coupling, or sometimes called the axion term, will rotate it by some amount. And the thing that's so delightful to me is that this is not the first time this has been discovered, even in the cosmological context. So if we go back to the paper of record once more, this is 1997, just about around Jim's birthday in 1997, about a week before his birthday. And what I always love about looking at old New York Times front pages is that like some of these people are still in the news. Like there's Newt Gingrich in the upper portion panel over there. Benjamin Netanyahu, he's over there on the left. Slobodan Milosevic is down there. But anyway, look at the lower right. And not only is are these political figures, not only are they time translation invariant, but also this phenomenon of claiming detections of cosmic polarization rotation of a Chern-Simons-like variety. They are also time translation invariant in that they come up every so often. And the question is, how do we apprise whether or not there's something to be learned from them? And how do we scrutinize them in great detail? I will even point out that it's not even the first time that we've claimed that the community as a whole has claimed a detection of this. In fact, it was claimed at a higher level of significance about 11 or so years ago, when a group led by three friends of mine, Jia Li and Zhang, claimed a 3 sigma detection using data from BICEP and WMAP and other projects. This was a 3 sigma detection. So again, Miyame and Komatsu are claiming 2.4 sigma. So this comes up a lot, and the question is, how do you deal with it? Well, they dealt with things in terms of the most pernicious of all effects that confront cosmologists making peregrinations into polarization. The most pernicious thing is calibration, and knowing that you're making an accurate measurement. For it is very difficult to get a calibration standard. There's no standard candle for polarization. It just doesn't exist in the universe. I call it a standard stick. It doesn't exist. So to the extent that you want to constrain a phenomenon that could produce a rotation of the intrinsic polarization by a tiny amount, only less than 20 or so arc minutes, that claim needs to be backed up by exquisite calibration and also systematic control. And they do so in a unique fashion. I won't get into too much detail, but they essentially are using the galaxy in a sense. They're using the Milky Way galaxy and the properties of foregrounds and claiming that the path length over optical activity of birefringence is insufficient in our galaxy to cause a rotation such as the type that was observed by Planck. You can see the data is rather noisy. And again, their data is not altogether consistent with the data that has been collected in the field to date, which is shown here, a collection that my graduate student Marty Navaroli made in his thesis. And so there's their data point at the end there. And they're claiming essentially that there is no calibration or systematic error on this. So this, they claim, is dominated, whereas some of the error bars that are shown with like a light blue in the center of this graph, we're accounting for both statistical and systematic errors. And so there's sort of a preponderance of evidence that led to the Jia et al. Claim that there's a negative cosmic polarization angle. Komatsu and Myanmar are quoting a positive rotation angle at 2.4 sigma. And even they themselves make the following claim. If confirmed, it would be a game-changing discovery. So I put up some of our objections to it above. And that's mostly for experts that may be watching in the field, but we are preparing kind of a response to this and also forecasting what upcoming experiments such as the Simons Array and Simons Observatory will do to limit and exclude, as I'll talk about, by doing calibration intrinsically separate from measurement of the CMB's polarization. So stay tuned for that. Let me first get to the Simons Observatory. So the Simons Observatory is perhaps the most ambitious cosmic microwave background experiment ever designed and funded, and is midway through or a little bit past the midway point in construction. I'm going to show you some video that we shot this morning on the construction here in the high Atacama Desert of northern Chile. So this is at 17,200 feet. And it's very hard to get people to go up there to actually work on a project like this. And so we had to take volunteers. And luckily, we got some good volunteers there. I don't know if you can see. There's a guy on the right in a red jacket, and he's not wearing socks. So that's Jim in Maryland. And so we put them to work, you know, because he's out of a job, I've heard, come June. And he'll be replaced by the guy in the orange jacket on the left at the foundation, who's also not bad at shoveling, but that comes from being around me too much. He shovels something else that's brown that I won't get into. But nevertheless, and there's Adrian Lee on the far left, who's our colleague and the co-PI of the Simons Array, as well as a spokesperson for the Simons Observatory. And we were shoveling, and it took, you know, I was going to update the final slide to say, you know, August 2019, but it only took a few minutes. They're surprisingly good. And Marilyn also just, she's just exquisitely coiffed, as you can tell there as well. So thank you to those laborers. It was quite enabling of them to be there. And we kicked off the Simons Observatory with that groundbreaking, and we've been constructing ever since. And as I said, I'm not going to talk about all the cool stuff that we really designed and pitched and sold the Simons Observatory on, because today's focus is primarily on this exotic phenomena, this cosmic birefringence of this Chern-Simons variety. So I want, yeah.
If there was a question that if you could clarify, the question is between which two directions the polarization angle is being measured.
So there's a convention that I'll just show on this slide. So if you take the meridian that goes from north to south, there's a polarization convention that's defined by the only union I'm a member of, called the International Astronomical Union, and that defines positive polarization angles as a clockwise sense about that meridian, and counterclockwise or left circular polarization would be the opposite direction. Does that answer, Greg?
Thank you. Yes.
Sure. Okay, so who are the smiling faces of the Simons Observatory? There they are. This was not taken last year, as you can probably guess. It's 2 years ago. We had our face-to-face meeting at UC Berkeley. There's over 300 people in this awesome collaboration. And I just have much more fun with them than we should legally be allowed to have. But here's a site, and here's a video. The audio is not critical, but I can hear it on my side. This is pouring concrete for one of the telescope's bases just this morning. So we're going to have 3 telescopes of this diameter, the Simons Observatory Small Aperture Telescope. And there it is. This is the middle of summer in the Southern Hemisphere in Chile. So it's even colder than San Diego is right now. So that's the exciting update. I can't resist showing my my students and postdocs and colleagues here at UC San Diego and the High Bay across from my office here. We are busily making plans for detector testing, detectors and readouts. Suzanne Staggs's group is leading that. She's our spokesperson of the Simons Observatory. And we have a matching telescope, the large aperture telescope. And that has been led by Mark Devlin's group, who's the third spokesperson. And he's at University of Pennsylvania. And they have a telescope that even I can fit in. It is enormous. It is about 3 meters in diameter. Just the camera and the telescope is comprised of 2 mirrors, each one of which is 6 meters in diameter. Just a phenomenal observatory. But again, I'm not going to talk about that because what I want to get to is really things that can be used as a probe of this exotic, perhaps revolutionary term known as this Lorentz violation effect, as manifest in the propagation of distant photons as they traverse the universe. Well, as you know, there are more photons than just the cosmic microwave background. And so to get a handle on whether or not such a claim could be relied upon, we want to look at as many different frequencies, as many different wavelengths as possible. And one of the ways that we can get a handle on both Lorentz invariance violation and parity violation is to use optical telescopes and use polarization of lampposts that we are going to explore very briefly here. And these are actually active galactic nuclei and exotic sources known as blazars that I'll talk about. The work I'm going to show very, very tragically represents the last work of my really good friend and close colleague, Dr. Andrew Friedman, who tragically passed away last summer in the midst of this, not from COVID, but he had a longstanding chronic condition. So unfortunately, he died very young. But he led this team, including myself and another colleague here, Professor David Teitler, David Kaiser, Grant Tepley is here, Gary Cole, who built the telescopes that you'll see, David Leon, graduate student who just graduated, Roman Gerasimov, Kevin Crowley, who's a current Simons Observatory graduate student at Princeton. Del Johnson is a project scientist or engineer. And then Isaac Browdy, I like to point out, he won the San Diego Science Fair, and he came in fourth in the state, California, in the state. He won the San Diego County Science Fair 2 years in a row, doing research with us into these exotic phenomena. And he was just a 15 or 16-year-old at the time. So, and he worked very closely with Andrew, who went to Berkeley as an undergrad, and Isaac is now an undergrad at Berkeley. So what are we trying to do with these optical measurements is look for what are called departures from the standard model. This has a name, this type of taxonomy is known as standard model extensions. So the Chern-Simons Lagrangian density I showed at the very beginning is but one example of hundreds of potential terms that could be added to the standard model, which incorporates both general relativity and the classical standard model of particle physics, cartoonishly shown above. And so the question is, what can you add to this Lagrangian that violates Lorentz invariance and parity, or CPT, it's charge, parity, and time reversal invariance, and so on, without violating current upper limits on such effects? So these can come from exotic phenomena, such as discreteness of space-time, extra dimensions, which has an impact on quantum gravity studies in some higher dimensional fields, such as ADS-CFT. And this might be perhaps our only window, no pun intended, on getting at these particular exotic phenomena through these very distant cosmic lampposts. Not as distant as the CMB, but distant nonetheless. And so, in some sense, some of these phenomena, just as, for example, as I claimed before, there's a motivation to look for a violation of parity in electromagnetism because electromagnetism is unified with the weak theory to make electroweak theory. And we know the weak theory, as Madame Wu showed us, is in violation of parity. So therefore, the full group may be in violation of parity. So that's why we might look for it. Well, what if there's a theory of everything, and there are all these breakings of symmetry, of parity symmetry? Then you might expect even gravity to violate parity. In other words, there might be different propagation velocities for left polarized gravitational waves, if you like, versus right polarized gravitational waves. Those are phenomena that we could look for. Those are, again, motivation, speculative, but we should look for it because this may be the only handle we get. So for these different coefficients, what we can look for are a variety of different objects. So one we can look for is vacuum dispersion, which is where the speed of light becomes energy dependent. And that means that a red photon might arrive before a blue photon. And you might say, well, we know that's not true. But how do you know it holds true over the course of the entire universe? The microwave background is a very narrow region of the electromagnetic spectrum. So what we did is look for this phenomena. Both we looked for this in what are known as eclipsing binary stars. That's actually what Isaac Braude won the San Diego Science Fair with. Was a test that we devised to set a limit on the difference in speed of light by noting the eclipse times for eclipsing binaries when one star passes in front of another, and noting that there was no change in arrival time of blue photons versus red photons, for example. But we want to do that over very large distances. That would then limit what's known as vacuum dispersion. Another way you can break the standard model is what's known as vacuum birefringence, which is essentially this Chern-Simons term. You could also have both terms. You could have vacuum dispersion and Chern-Simons. So you can modify it, and all the different permutations you can get, we are looking to limit. And they can also depend on the dimension of space-time and the dimension of the energy operator to very high powers. So formally speaking, it's an infinite Taylor series of terms that we limit, but we restrict ourselves to the most plausible ones. So on the right, you can see the combination of polarization being both energy dependent and the dispersion rotation being energy dependent and also distance dependent. So the more time spent in this optically active medium, the more rotation would take place. So you start off with these beautiful black arrows at the top, which is just representing the sum of all the colors. They're all not rotated at the emission source. And as they propagate downward to the observer, different frequencies propagate at different, rotate their polarization plane with different phase velocities. So you end up getting the smeared out arrow. Effectively, you get some depolarization as well. And I should point out that all these effects could be isotropic, or they could vary in space and time as we look. And so you'd see a patchiness to this phenomena as well. If you look for this net effect in the lower column that's marked total, I think it kind of looks like this guy, Bart Simpson. But you know, who am I to say? So we looked for this phenomena, and we actually did an incredible job at limiting the amount of Lorentz invariance violating and CPT violating effects. We saw a limitation on how big such an effect could be and evade our constraints by using multi-wavelength observations with small ground-based telescopes, looking over a very wide redshift range, pretty close to, you know, some of the, I mean, the world record or universe record for redshift is over 10 now, but we did find some that are quite high, and assembled the most complete catalog ever, and it's available for public consumption. So we use these active galactic nuclei. They're called blazars or AGN. We looked at a particular type of one called the BL-LAC object. They're highly polarized. They're variable. They're very interesting phenomena. They're powered by black holes at their center. And we use what's called spectropolarimetry, which is a fancy word for we measure their color and we measure the polarization properties simultaneously. The fact is that we did it with a small telescopes, plural, and you'll see how we did that in a configuration that our colleague, Gary Cole, who's just an independent astronomer, an amateur astronomer, but one of the best astronomers that I know, he assembled a receiver array called the Array Photopolarimeter, or APPOL, and we used it to set extremely competitive constraints on such exotic physically violating effects. So here's a schematic of the diagram. You basically get this birefringent calcite object that I showed you before. We use that, and we use its properties to disperse a beam of starlight, or BL-LAC or AGN light, to appear in two different positions. And then we modulate the polarization with what's called a half wave plate, exactly what we do with the Simons Observatory, as we will with the small aperture telescopes. And then depending on where how polarized these objects are, we get a difference in the polarized intensity. And this is each spot on the right is the same object, just dispersed into two different angular positions, which then disperses it on the CCD chip. And so we use that and we extract the polarization for a host of stars. We did that, and we did that on a very small array of telescopes. These are just amateur telescopes that Gary has lovingly assembled into an extremely exquisitely precise network array of cameras. And we actually set competitive upper limits on some of these effects. Competitive with what? Well, competitive with 3.6 meter class cameras. And so this is really a pathfinder for eventually proposing to use big telescopes like the Isaac Newton telescope and the Canary Islands and some other optical telescopes. So we set limits on this over a year ago. And then just recently, and with the summer, after Andy had tragically passed away, we were able to get another paper published in his memory. You see that on the right. That's one of my proudest accomplishments of the past few years, is to see Andy's work through. It's really, the paper is a tour de force. He was such an amazing, inventive, creative titan of a young man. I'm still quite emotional thinking about him. But we were able to get it published in his honor, and you can learn more about him. I implore people to go to his website here at UCSD. It's really just mercurial and fun, just like Andy was. So the results, just to summarize, these optical lampposts, these lampposts that you can measure using amateur class telescopes. We assembled this enormous catalog on the lower left. We mapped out the polarization properties by morphology and by class of object, ranging from QSOs, GRBs, Seyfert galaxies, and the BL-LAC objects. We plot their polarization angles. This had never really been assembled in such a comprehensive form. So very proud of that. That's publicly available. You can contact me if you're interested. And Gary upgraded around his telescopes, which is equivalent to a 0.5 meter diameter telescope in terms of aperture size. And we're already, as I said, competitive with the previous upper limits were set by 3.6 meter class telescopes. And the reason that we can do that is because we have extremely broadband coverage and extremely high polarization fidelity in those broad bands. And so there are other aspects that we're looking to further investigate with collaborators, Fabienne Kislat and others around the world. Okay, last thing I want to point out is some work being done by our colleagues on the Simons Observatory in the future of this field. And that revolves around the fact that it is impossible, as Myanmar and Komatsu point out, it's really impossible to disentangle, to separate out the effects of a miscalibration of your polarization orientation sensitivity in your detectors. You can't separate that out from a cosmic birefringent effect. So in other words, the same effect that converts an E mode pattern at the top to a B mode pattern can come about either because there's Chern-Simons vacuum birefringence, or because you've miscalibrated your detectors. So you want to do a good job at each of those. Myanmar essentially used the galaxy and some of its properties and its stability with respect to this effect, use that as a way of calibrating, et cetera. But we have some comments on that particular choice, as you'll see over the coming weeks as we prepare our response. But you'd like to be able to do the calibration sort of in-house, and there's a variety of different ways to do it. But again, there's no standard stick. There's no polarization calibration standard you can go out and measure. And that's very radically different from the CMB temperature measurements done by, say, Planck, where Planck can look at a planet like Jupiter, and we physically have been to Jupiter. We've stuck thermometers in Jupiter, if you like. We know how far away Jupiter is. We know how big it is. So it can be an absolute temperature calibrator. But we have no such analog for polarization calibration. We have other objects, celestial and human-made, but they all have deficiencies that we're trying to improve upon. So our collaborator, Rolando Dunner, and he's in Institute of Faculty of Physica. He's at Pontificia University, which is in Chile, and he's a long-term collaborator with the ACT team and with our team on Simons Observatory. And he's developed a very, very cool and fun project using a commercially available drone. And this drone will spray out a polarized signal that Rolando's team can track exquisitely accurately. And so it's just kind of a cartoon of what he will do with this. And he's already done a prototype measurement that I'll show you in a second. And essentially, he can reconstruct the angle that the drone is at, the angle that the ground subtends from very high accurate photogrammetry, which is precision measurements using photographs. And he can do that to very, very high resolution and very high precision. He's already mapped out and made a very an exquisitely executed map of the Simons Observatory's closest neighbor, which is the ACT telescope. You see that here, and here's a closer view of it. So there's the drone, And he sent me this cool video. Rollo, he might be watching. I don't know if he's watching, but if he is, thank you, Rollo, for sending me more footage. This is has no sound, so don't worry about it. So this is one of his collaborators, and they're setting up the drone, and now it's going to take off. Now it's flying over the ACT telescope, and you can see it down there. And this is highly sped up, but actually it's very stable over the time we need to spray out 100% polarized, linearly polarized signal into, say, the ACT telescope, or eventually into the Simons array and Simons Observatory telescopes, and use that as a standardizable stick. So a polarization reference source that we can trace exactly, so that we don't need to make assumptions about the foregrounds or assumptions about tau A and other objects. So this could be used as a highly, highly precise and accurate measurement that we can then calibrate our measurements. And then we won't have to worry about, is this a deficiency that we're measuring in our instrument, or is it truly a Chern-Simons cosmic birefringence-like term? So final few slides are going to plot where are we going next in the field. And I thought I'd show this. Oh no, this is actually the price of GameStop stock. Sorry, my stockbroker put that in by mistake. Actually, here we go. These are publications on the Chern-Simons cosmology topic. If you just search the archive, I stopped this in 2014. Actually, my student Kelsey Lund stopped this, but actually it goes up like a hockey stick, not unlike GameStop stop. So hopefully Renaissance is all over that. But it's going up at this hockey stick-like rate. This is incredibly exciting. And the reason it's exciting is that we suffer from an extreme set of diverse neuroses in cosmology, only some of which I've put here. But about every day I could plot a hockey stick-like plot like the previous slide, showing all the things of tensions and cosmological crises. Here's some. There's even one on the right with Adam Rees and a Hubble constant crisis. Some guy named Brian Keating put that slide together for my podcast. So we do talk about this, but there are some really interesting, outstanding questions. Remember the very beginning of the talk, I claim that most of the revolutions, quote unquote, in opposition or contradistinction to Kuhn, I would say that most of the paradigm shifts that we're seeing is really going from crisis to crisis. So Weinberg said that physics itself thrives on crisis, and he said there weren't that many back then. He lamented it, but today we have a lot of them. And what's interesting to me is that many, if not all of the crises, plural, that we suffer from could be cured not by a high-priced therapist, which I've often claimed, many of my colleagues need, but actually by such measurements as I've described today. Namely, the polarization measurements as we do with both optically polarized lampposts in the form of blazars or other objects, and the CMB's polarization can also shed light, no pun intended, on effects that could resolve, for example, the Hubble tension, which could be resolved by so-called primordial magnetic fields, PMFs, that we've done some work on in the collaboration, and we will continue to set exquisite limits on using the Simons Observatory and Simons Array. We can ask whether or not this hint of cosmic birefringence, parity violation electromagnetism would, it would be a crisis in the sense that, would have to rewrite a lot of our textbooks. Jackson would have to be rewritten at some level. But of course, these are opportunities. These are crisopportunities, as Homer Simpson might say. And so what I think about is how much we can contribute, even if you just look at the things that we're not considering the top line motivation for the Simons Observatory or for this APOL astronomical observatory. We can shed light on things ranging from dark energy to dark matter. One of the original motivations for adding these terms, as Witten and Turner and Sikavy showed decades ago, Sean Carroll, was for axions. Well, axions are considered to be one of the most prominent leading candidates to explain the dark matter, the missing matter that we observe its absence, its lack, in the measurements of the universe's matter density. So that's an exciting thing that we will shed light on with the polarization of distant objects that I've been calling these lampposts. And the last question, I think, is the most delightful, delicious one of all, and that's whether or not Lorentz invariance is sacrosanct. Every week or so, I get an email. Professor Keating, Einstein was wrong. I can prove it. I'm not very good at math, but if you do help me, I'll share my Nobel Prize with you. And I actually told that to Adam Rees over there on the right, and he said, "Yeah, how do you think I won my Nobel Prize?" But actually, it may be that Lorentz invariance is only an approximate symmetry, a partial symmetry that is not completely respected throughout the longest baselines that are accessible only to these distant, drunks searching for lampposts that are far off on the cosmic horizon. So with that, I will leave you and ask you to stay tuned for upcoming programming, virtual for now. Hopefully this will be in present. They promised me wine and cheese. I gave you some cheesy puns and I whined a lot, and I'm happy to take questions from Greg and from the audience. Thank you guys.